Welcome to today's central exercise session. In this session, we'll be discussing exercise sheet number 10, and that is mainly about limits and continuity of functions. As usual, please ask your questions at our chat channel at chat.tum.de, and please use this channel here, MA9711-CE. As always, the chat will be moderated, and today's moderator is once again Leslie Fernandez.
Hello, everybody, and welcome to the central exercises. So, as we have been proceeding the whole course, we're going to get the questions in the chat, and then I will bring them to the webinar whenever there is time for that. Remember not to write your questions in the chat, in the Zoom chat, because we do not really check that one. Yeah.
And also, we're not looking for raised hands or something like that. So please just use this chat channel, ask your questions there. We'll be happy to respond. Okay, so let's start right away. As I said, sheet number 10 is mainly about function limits. And the first question is one about function limits, kind of a warmer-upper for function limits. So let's have a look at C10.1 first. Now there's two subproblems here. The first one asks for the limit of a rational function. So we want to compute the limit of the function x to the third minus 7x plus 6 divided by x squared plus x minus 2. And that for x tending to 1. Now, the first thing that you usually do if you want to compute a function limit is you just substitute that value for x and see what happens. If you have finite values in both numerator and the denominator does not happen to be 0, then you have your function value and you're fine. So in this case, if I substitute 1 for x, then what I get in the numerator is 1 minus 7 plus 6, so that is 0. And in the denominator, I get 1 plus 1 minus 2, which is also 0. For the numerator, 0 will be fine. For the denominator, obviously, it's not. So 0 divided by 0 is just not defined, and that means we'll have to find another way. What we have also seen by doing the substitution is that 0 is a root of both the numerator and the denominator. 1 is a root, not 0. 1 is a root of both the numerator and the denominator. And that means we should be able to factor out the factor x minus 1. So both numerator and denominator are polynomials. And for a polynomial, we can always factor out the roots in this form, like x minus 1, and then some polynomial that is left. And the same will be true for the denominator. We have x minus 1 times some polynomial that is left then. To find out which polynomials these two are, one thing we can do is polynomial division. So just for practice, I try to demonstrate that for these two polynomials here. So for the first one, we have x to the power of 3 minus 7x plus 6, and we want to divide that by the polynomial x minus 1. Now what I do is I'm trying to find a factor that multiplied with x yields exactly that leading factor here, x to the third. Of course, that factor will be x squared. Once I figure that out, I'm going to multiply that factor with this one and subtract the result from my original polynomial and see what's left. And then I'll continue with this process until only 0 is left. And of course, that has to happen at some point if that division actually works. If it doesn't happen, then something is off. Either I miscomputed my root here, and maybe this is not even possible, or I made a mistake in this division. So let's see. So we have this x squared times x minus 1. So there is x to the third minus x squared. and we're going to subtract that here. So what we get is x to the third minus x to the third, that's a 0, minus x squared, and there's no x squared up here. So that will yield x squared. And then, of course, we still have this minus 7x plus 6. So that's the remainder for now. And then I'm going to repeat the process. So I'll now find something that multiplied with x yields x squared. And of course, what I need to find here is just x. And I'm multiplying x with that whole factor, x minus 1. So that yields x squared minus x. And I subtract that. Okay, so if I do that, x squared minus x squared cancels out. Then I get minus 7x plus x. Remember minus, minus? Yeah, so this is plus x. So minus 7x plus x is minus 6x. And I also have that factor plus 6 that is left here. And then final step. Again, I find a factor that multiplied by x yields minus 6x. And that factor is, of course, minus 6. So multiplying minus 6 with this factor, x minus 1, yields minus 6x plus 6. And again, I subtract that from the remaining polynomial, and that yields a result of 0. So I'm done with the polynomial division. And that means I factored this polynomial here, or at least part of it. So x to the power of 3 minus 7x plus 6 is the same thing as x minus 1 times x squared plus x minus 6. Okay, that was the first part of that, and we have to do the same thing for the denominator. And of course, there are other means to get that, but just for practice, we once again do this polynomial division thing. So here we have x squared plus x minus 2. And again, we want to divide that by x minus 1 as a factor. So we find a factor that multiplied by x yields x squared. That is, of course, just x. Then we multiply x with this factor here. So we get x squared minus x. And we subtract that from the original polynomial. And that yields x squared minus x squared is 0. Then we have x plus x, that's 2x. And we still have that minus 2 factor up here. And the next factor I need is 2. So because 2 times x is 2x. And if I multiply 2 times this whole factor here, then I get 2x minus 2. And I subtract that from the remaining polynomial, which yields 0. So I'm done. And again, that means my original polynomial, x squared plus x minus 2, that can be written in the form x minus 1 over x plus 2. Okay, and now we are ready to put this all together. So basically, after this little intermission here, we have our limit. Let me write that down again. Limit of x to the third minus 7x plus 6 over x squared plus x minus 2 as x tends to 1. Now, we just factored out x minus 1 here. And the result was, let's see, x squared plus x minus 6. And for the denominator, we get x minus 1 times x plus 2. So as we can see, these two factors cancel out. And that, of course, was the whole purpose of this exercise here. So we are left with the limit as x tends to 1 of x squared plus x minus 6 over x plus 2. And now, again, if we try to substitute x equals 1 into these two functions in the numerator and then the denominator, what we get is 1 plus 1 minus 6, so that's minus 4. And 1 plus 2, sorry, plus 2, and that is 3. So altogether, we can just use these values and get our limit. So the limit is minus 4 divided by 3. And that is the first limit of this exercise sheet. Questions about this one?
Yeah, so there are some questions related to this exercise. So the first one, and maybe the one that it was repeated many times, is whether it's possible to use L'Hopital's rule.
In principle, yes. Of course, you could use L'Hopital's rule here. I mean, you have a limit of the form 0 divided by 0, and that means you could just use L'Hopital's rule. The purpose of this exercise sheet is mainly to show you methods that work without using L'Hopital's rule. For two reasons. First and foremost, I'd like to demonstrate these other methods to you because at some point it might be necessary to use them if L'Hopital's rule doesn't work for some reason. But maybe these methods still will work. So it's necessary to know about these. And on the other hand, we have not even discussed differentiation yet. So we don't officially know what L'Hopital's rule is. We will, of course, get to know that in one of the upcoming videos. But in case you never heard of L'Hopital's rule, don't be worried. We'll discuss that and we'll have problems on L'Hopital's rule as well. And this is one that can be solved using L'Hopital's rule once we've had that in the lecture.
Yeah, okay. Then another question is, well, let me first make a remark. Even if you use L'Hopital's rule, the result is still minus 4 divided by 3. So if
of course, the result should still be the same, yeah.
Yeah, so I mean, because it's mentioned like, can I use L'Hopital because I got 3 for A, then it's wrong. So I mean, if you use L'Hopital, the result it should be still the same.
If you use L'Hopital correctly, then you will get the same result. If you don't get that result, then you did something wrong.
Yeah. Then there is a question, is there a way you could explain how the polynomial division in general works because it's no longer part of the curriculum for the A levels in Bavaria?
Didn't I just do that? Maybe you could specify what more explanation you would like?
I think like maybe like in big lines, we can say that first of all, like x minus 1 was obtained because we know that 1 is a 0 of both polynomials. Mm-hmm. And then you just have to divide it. Like one polynomial by x minus, I mean, both polynomials by x minus 1, I guess. I'm not sure whether this person is expecting like a more general explanation or maybe like ask it again if it wasn't.
Yeah, maybe you could specify that more precisely if what part needs more explanation. And I'll also try and explain that in more detail in the suggested solutions. Yes, good point.
Then it says, why did we factor out x minus 1?
Because that seems to be the problem here. So we found out that both the numerator and the denominator were 0 at x equals 1, right? And that means 1 is a root of both numerator and denominator. And that already suggests that it's possible to factor out x minus 1 and then cancel that factor out. So hopefully that will get rid of the problem. It doesn't have to, of course. There might still be other problems with that limit, but at least this one problem should go away. And that's the reason why we factor that out, because we want to be able to cancel it out later on and get rid of that 0 by 0 problem.
Mm-hmm. And then for all of you that are asking about the L'Hopital's rule, I mean, as it was mentioned, it will come in the following videos at some point.
Yeah, we'll discuss L'Hopital's rule some more, but again, the purpose of this exercise sheet is to discuss methods that work without invocation of L'Hopital's rule. So I suggest you try the homework as well. You try that without L'Hopital's rule explicitly, because you should be able to use these methods as well.
Okay, then there is a question. It says, will there be a case where it's forbidden to use L'Hopital's rule in the exam?
That may be the case, yes. Yeah, for example, something like homework 1.5, I think, or 10.5, I think it is, that explicitly says compute the limits without using L'Hopital's rule. But of course, I want a justification for the limit, and if your justification involves L'Hopital's rule, then that will probably not earn you any credits in the exam. That might be the case.
No more questions.
Or just to add to that, maybe even more, maybe even meaner, there might be a limit that suggests that L'Hopital's rule might be possible, but for some reason it's not possible to use it. So if you try to use it and kind of fall for that trap, then again, you might get 0 credits. So you should be prepared to compute limits without invocation of L'Hopital's rule. So let's go for part B then. Now here's another limit as x tends to infinity this time. And we want to compute the limit of x minus the square root of x squared minus 6x plus 25. So in this case, if we just substituted more or less infinity into that equation, we get something like infinity minus infinity. And yeah, basically anything can happen in that case. So we again have to find some reformulation for that. And there's a standard trick for expressions like that one that have a sum or a difference that involves a square root, like here. And what you do is you use one of the binomial theorems. The idea here is basically to take this expression, multiply it by 1, and then write this 1 in a more complicated way. So we multiply this by 1, and specifically we will write this 1 so that we can apply a binomial theorem. So we take this factor here, and then instead of 1, we just write x plus the square root of x squared minus 6x plus 25. So we basically copy that expression and then divide by that expression so that we could cancel that out. And that's what I mean by writing 1 in a more complicated, complex way. Basically, 1 is equal to this expression here. Yeah, and please note that we have replaced the minus by a plus here. And that's the whole point of this method here. What we do is we reformulate this in a way that enables us to use a binomial theorem up here. And you will hopefully remember that theorem. Specifically, we're trying to invoke a minus b, a plus b is a squared minus b squared. Right, so this here is an expression of the form a minus, that square root is then b, and here we have a plus b. Right, and what happens if we do this is we can now reformulate this to read a squared minus b squared, and of course the squared will get rid of the square root. That's the whole point here. So what we get is x squared minus that square root squared, and that is x squared minus 6x plus 25. And of course, we still have that square root in the denominator now, so we didn't entirely get rid of it. But let's say it's packaged more nicely because we have a plus now, right? And if x goes to infinity, and this goes to infinity, and well, we cannot really be sure about this. There's a minus in there. But if we add these two things, once we find out what they are, that might be easier to subtract things. But we'll see about that. Yeah, let's just go on and see what happens. At least we simplified the expression in the numerator somewhat. And now what happens here is if we try to simplify even more, we'll see that x squared minus x squared cancels out. And we're left with just 6x x plus 25 over this square root expression here. And now again, we are able to use a standard method. Namely, we can divide by the highest power of x. The highest power in the numerator is obviously x. There's only one variable here involved. In the denominator, we also have x, and we have x squared, but under the square root. So square root of x squared is also x, of course. That means we try to divide this whole expression by x. And in doing so, we get 6. And I think I made a mistake here. Yes, I did. I'm sorry.
Minus 25.
Yes, thanks. I just noticed that. So that should be a minus 25. Sorry. So we get 6 minus 25 over x. And in the denominator, we get 1 plus and the square root. And we also need to divide that by x. So if we take that x into the square root, then we divide everything in the square root by x squared. So we get 1 minus 6 over x plus 25 over x squared this way. And now let's see what happens if x tends to infinity. And this fraction here will tend to 0. These two will also tend to 0. So what we are left with is a 6 in the numerator and a 1 plus square root of 1 in the denominator. And that's just finite numbers that we can write down. So what we have here in the limit is 6 over, or square root of 1 is 1. So 1 plus square root of 1 is 2. So we get 6 over 2 or 3. And that means the limit here is 3. Okay, let's open this for questions.
So far, there isn't any more question than the minus 25 correction.
Okay, wonderful. Good, so then we can move on to 10.2. So let's do that. C10.2. In 10.2, we have a function f, which is defined on the interval from 0 to infinity. So all positive numbers, maps to R. And the definition is piecewise. So we have 3 different cases here, specifically. In the interval between 0 and 1, strictly, the function is defined as x minus 1 over x squared plus 1 for 0 less than x less than 1. Then at the point 1, the function is defined as 2. And for numbers larger than 1, the function is defined as x to the 3rd power minus 1 over 6 minus 6x. And you will notice that this denominator here does not have any real roots, so that's not a problem. This denominator here does have a real root, which is 1. 1 is explicitly excluded here. So again, not a problem. So this definition really works. And the question here is, compute the left and right limit of the function f for x tending to 1, and is the function continuous at 1? Now, let's start with the limits. So the first thing we do is we want to compute the limit of f of x as x tends to 1. And let's say start with the limit from the left, so from below. X tends to 1 from below. That means we can assume that the values of x are less or equal to 1. So what does that mean for the limit? Well, that means as long as x is less than 1, we will be in that case here. So all the rest does not really matter for this limit. And that means the definition that we should use is this one here. So we want to compute the limit of x minus 1 over x squared plus 1 for x tending to 1 from below. Now, if we do so, we can easily just try to substitute the function, the values. So we can substitute 1 for x and see what happens first. If we do that here, that tends to 1 minus 1. And in the denominator, we get 1 plus 1. So that goes to 0 over 2. And well, 0 over 2, that's just fine. That's 0. So no extra work to do here. The limit is 0. Then for the limit from above, so x tends to 1 from above, that means now we can assume that x, in taking that limit, that x is always greater than 1. And that means we are in this case here. So the definition, the term for the function f that we should use in this case is this one here. So let's do that. And we get limit as x tends to 1 from above, x to the third power minus 1 over 6 minus 6x. Now again, if we try to just substitute 1 for x in here, we get 1 minus 1 and 6 minus 6. So we get something of the form 0 divided by 0. And we're back in basically the case of 10(1)(a). So we know that 1 is a root of both polynomials. And we cannot compute the limit right away, but we can again try to factor out x minus 1. Now for the denominator, that's pretty easy. So let's write that down right away. For the denominator, basically, we just have to factor out 6 or minus 6. So here we get minus 6, and then we have x minus 1. For the numerator, just for practice, let's try again to divide this polynomial by the linear factor x minus 1. So we have x minus 3, and we want to divide that by x minus 1, or as an alternative way of expressing it, we want to represent that polynomial in the form x minus 1 times something, and we're looking for that something. Okay, so what do we need to do? We first look at this leading factor here, and only the leading factor. So this is only x here. And this leading factor, x to the power of 3. What we do is we find something that multiplied by x yields x to the power of 3. Obviously, that needs to be x squared. So x squared multiplied by x is x to the power of 3. Once we have that, we subtract this factor times this factor from our original polynomial. So what we do is we multiply x squared with x minus 1. That will be x to the power of 3 minus x squared. And then we subtract that from the original polynomial. What we get is x to the power of 3 minus x to the power of 3, that's 0. And then we have plus x to the power of 2. There's no x to the power of 2 here. But there is a minus 1 here. So we're left with x to the power of 2 minus 1. Now let's continue that in the same way. Again, we have to find a factor that multiplied by x now yields this leading factor here, x squared. And obviously, that factor must be x, right? So x times x is x squared. X times x is x squared. And now we again subtract x times this whole factor from our remaining polynomial. So x times x minus 1 is x squared minus x. X squared minus x. So we're going to subtract that. And we're left with x minus 1. And now finally, we need to find something that multiplied by x yields x. Well, that of course can only be 1. And then we subtract 1 times this factor from our remainder. So we subtract x minus 1. And of course, x minus 1 minus x minus 1 is 0. So we're done. Or in other words, if we transfer this here, then this means we can decompose this polynomial into x minus 1 and this remainder here. And that is x squared plus x plus 1. So if we use that, can I use that up here to get x minus 1 times x squared plus x plus 1. Like this. And again, we are in a situation where we can cancel out this factor here. So to continue with that computation here, we get the limit as x tends to 1 from above of, we cancel that out, we have x squared plus x plus 1 in the numerator and minus 6 in the denominator. And now if we let x tend to 1, that will only involve the numerator. So that will tend to 1 plus 1 plus 1, which is 3. So we get 3 over minus 6, or minus 1 over 2 as our limit. Okay, so we have computed both one-sided limits from below, from above. To sum up, what we found out is the limit of f of x as x tends to 1 from below, that was 0. The limit of f of x as x tends to 1 from above, that was minus 1 over 2. And that specifically means the limit of f as x tends to 1 does not even exist. Right? So the two one-sided limits don't agree, or one of them doesn't exist, then of course that limit cannot exist as well. The limit of a function exists if and only if both one-sided limits exist and agree in the value. So this limit does not exist. And final question, continuity. Continuity would mean the limit has to exist and it has to agree with the function value. As this limit does not even exist, let alone agree with the function value, whatever we set it, this function is surely not continuous, and it is not possible to change it in a way to make it continuous at just this point here. Okay, so that also means f of x is not continuous, and that was not asked in the problem, but just to add this information, it is not possible to change the function value f of 1 in a way that would make the function continuous. Right, so what happens here is there's a real jump, if you want, from one side to the other. So basically we have qualitatively a behavior that is something like a function that approaches, that point here. Then there's a jump, and the real function value is somewhere else at that point. Yeah, but there is no way of setting a function value here at x equals 1 that would make the function continuous. The two possible choices that would be best would be either setting it here or here, but there is no value that would satisfy both sides. So these are just disconnected. Okay, that completes 10.2. What questions are there about 10.2?
Yeah, okay, so one of the first question, it's maybe a little bit of general concept, but I think it's important to clarify what is the difference between limit computing and convergence?
Limit computing and convergence. So basically, convergence means there is a limit. If a function converges for x tending to a certain value, then there is a limit of that function. And to find out what that limit is, we can try and compute it. I don't really know if you got the question correct, though. Maybe you mean something else.
No, I think that this is what it means. But I mean, like it might be, you might be asked to analyze the convergence, and of course, computing a limit is the tool that you have for that, right?
Or yeah, there's one tool, and for functions, there's not a lot that we could do otherwise, or not a lot that we discussed that we could do otherwise. Of course, it might be possible to prove that a function converges, meaning that there is a limit without actually having that limit, without being able to compute it. Yeah, you might be able to express that limit in a way that ensures there must be a solution, but you cannot possibly compute that solution. Think of sequences. Yeah, we had cases like that with sequences in series. For example, if you use the ratio test for a series, you maybe can be sure that series converges, but it still doesn't give you an information on the limit. And maybe computing the limit is not trivial at all. Things like that might happen for functions as well. But basically, we didn't discuss a lot of tools for that. So basically, the tool we have is actually computing the limit, or trying to compute the limit and failing maybe.
Another question is, if it couldn't say compute the left and right limit, would it be sufficient to compute one of the one-sided limits? And if it does not equal to, this is proof for it to be not continuous?
So if the question only was, is the function continuous, then yes. Yeah. So you can compute one of the one-sided limits, choose whichever you want. And if it doesn't happen to agree with the function value, then the function cannot be continuous, whatever the other one-sided limit may be. Yeah. And regardless of whether the limit actually exists or not. That's right. Yes.
I think there is another question that it might be a little bit of confusing. It says, so if we plug the given x value into the function and get a 0 in the denominator, then that is actually not the limit, and we thus have to use a different approach. And I tried to explain it, for instance, like taking the function 1 over x, that in this case, like you have 1 over, like when x goes to 0, maybe we can make like a couple of examples.
Yeah, we can just discuss it with this example. So if we have f of x equals 1 over x, and we want to compute the limit as x goes to 0, let's do the one-sided limits, right? So actually, that's nice. That function will show up in 10.3 anyway. That would spare some work. So let's discuss the limit as x goes to 0 from above. Then what happens here? So we have the limit 1 over x goes to 0 from above. That means, in particular, x is positive, right? If x is positive, then of course 1 over x is also positive. But as x becomes smaller and smaller and smaller, this expression 1 over x becomes bigger and bigger and bigger, right? Let me write that down. So x becomes smaller. That means 1 over x becomes larger. And of course, that growth is indefinite. So you can always make x a little smaller, but still stay above 0. And then 1 over x will grow bigger. And there's no limit to that. For every possible bound, so let's say, assume b was a bound for 1 over x, meaning 1 over x would be less or equal to b for all x. Well, can we prove that this cannot be true? Well, of course, we can do that. We just have to make x sufficiently small. What that means is, well, 1 over x is less or equal to b if and only if 1 is less or equal to bx. We know that we know that x is positive, so we can do that. And that in turn means we have to choose x greater or equal to 1 over b for that to be true. And that also means if we choose x smaller than that, then it will not be true anymore. So if we choose x equal to, let's say, 1 over b divided by 2, then that means x will be smaller than 1 over b, and that means 1 over x will be greater than b. And you can do this for every arbitrary b. So every bound b will be exceeded by a small enough x. Basically, that's the argument behind that. And of course, you don't need to repeat that argument anymore from now on. So all we need to know is that 1 over x can become arbitrarily large as x becomes arbitrarily small. And that means, in other words, this limit here is going to be infinity. And as we can be sure that this is always positive, the limit will be plus infinity. On the other hand, if we compute the limit of that same function as x goes to 0 from below, like this here, then we can be sure that x is negative. But if x is negative, this is also negative. The other arguments apply in the same way, so this expression still goes to infinity, but now we have a negative expression, and that means it goes to minus infinity. Okay, so this is minus infinity. And that again means the limit for x to 0 does not exist. And strictly speaking, of course, you would have known that from this point on, because a limit of infinity does not exist. A limit only exists if it has a finite value, right? So at this point, we could already have stated that limit for x to 0 cannot exist because one of the one-sided limits does not exist already. So I hope that was what you actually wanted to discuss.
Yeah, maybe like quickly we can also do like the example x minus 2 divided by x when x goes to 0.
X minus 2 divided by x. X goes to 0 on this one here. Okay, so if you do this one, what you can see is that when x goes to 0, this here goes to minus 2, obviously. The numerator goes to minus 2, so that's fine. But the denominator goes to 0. So basically, we again have a situation where we have a finite number divided by 0, and that must be some form of plus or minus infinity. So again, what we'd have to do is we'd have to look at the one-sided limits. Let's start with the one from above. So x is positive. That means the denominator is positive. The numerator, however, as we close enough to 0, the numerator will be negative. So we have something negative divided by something positive. And that means this should go to minus infinity. And if we're looking at the limit from below, x minus 2 over x, basically the argument is the same. As we're close enough to 0, this will be close to minus 2, the whole numerator. This will now be negative. So we have something negative divided by something negative, and that means we'll get plus infinity. And again, of course, the same argument applies that this will exceed every bound. Is that what you had in mind?
Yeah, perfect. I think now it should be clear for the ones who were discussing that. Let's continue with questions that do we have to show the long division in the exam, or we can find the factors in our mind directly and write it?
That depends on how complex the expression is. So I'd say for a quadratic expression, I'd say you can do this in your mind. That's fine. You don't have to do long division. For other polynomials, I'd rather you write it down so that we can actually be sure that you know how to do that and you know how to come up with the right result, and that you didn't just use your calculator or maybe a tool on the web.
Again, there is another question about more concepts like limit that does not exist as left limit is 0 or left and right limit is not equal. What is reasonable for a non-existing limit?
What is reasonable for a non-existing limit?
I think if like the limit is 0, then it's 0. I don't think that
Yes.
there is anything
So
you can say.
if the limit is 0, it's 0. So non-existing limit, basically, that could mean different things. That could mean the limit doesn't have a finite value, so it's plus or minus infinity, or it might not exist in the way that it is not even plus or minus infinity. Yeah, think of functions that oscillate. For example, if you're looking at a function like the sine, yeah, that oscillates between plus and minus 1, and then you try to compute the limit for that. As x tends to infinity, you will not get a reasonable value for that, right? It's always between plus or minus 1, but it constantly changes. So the limit for x to infinity in this case would not exist. And also, if the left and the right-hand sided limit do not agree, then also the limit does not exist. Limit always means you have to be able to approach that point from both sides and get the same value. Basically, that's what I can think of for non-existing limits.
Now, there is a question that it says, and I think we cannot really answer because it says, I factor out the entire denominator, 6 minus 6x, and receive minus 1 over 6 as an answer. Why does my method not yield the same answer? Well, if we don't really see it, I don't think we're going to figure it out.
I'd say it sounds like this should work, so you probably made a mistake in your computation somewhere. Feel free to try and post that to the Moodle forum, and we can have a look at that.
What would be if 1 leads not to 0 in the denominator?
Sorry, if 1 leads not to 0. So if, let's scroll back a little. So what you mean is, what if this would not tend to, so like if we had 7 minus 6x, for example, this would tend to 1, right? Now, if that happens, then basically you're done, because all you have to do is substitute 1 for x. You get a finite value here that is not 0, so we can just do this computation, and we get a finite value here. So basically what you have is a limit of this function divided by a limit of that function. And the limit of the quotient of two functions is equal to the quotient of the two limits, provided those exist and provided the denominator is not 0. We've had that as a theorem in the lecture. So if that is not 0 but 1, then you would just substitute and say, well, that's 0 divided by 1, so 0. And we're good.
Now there is a question, is there an easier, more obvious way to compute the factors for x minus 3 minus 1? So it's x minus 1 times x squared plus x plus 1.
Well, basically, I mean, we use that in the lecture multiple times, right? So it's kind of obvious what the result is here. If you have something like x to the n minus 1, then you can always factor in that way. You can always factor out x minus 1, and the remainder will always be x to the n plus x to the n minus 1, and so on, plus 1. So it's just a special case of what we did in the lecture before. But otherwise, I couldn't really think of something easier here.
Now, the last question is, how do we check whether the function value and the limit is the same?
Well, you compute the limit and you compare it to the function value, which either is given explicitly, like in this case, or which you also compute if it's not given explicitly, and then you compare them.
And just as a comment, there are some questions not related to the central exercises. I will collect them, and if there is some time at the end, I will bring them. Otherwise, maybe ask them in the question and answers forum.
Mm-hmm. Yeah, we try and go over those at the end if we have time. Otherwise, I can also go over the chat afterwards and see if I can answer some there. And of course, as always, you're welcome to ask your questions in the Q&A sessions or in the tutorials if maybe the chat is not the right place to have them answered.
No more questions, so we can continue.
Good. So let's continue with 10.3, I think. So here we have a function of the following form. F of x is 24 minus e to the power of minus 1 over the absolute value of x divided by 2. And the first task here is to determine the maximum domain of f. So we want to know where f can be defined reasonably. Basically, we have to watch out for functions that may not be defined anywhere. The exponential function is not a problem. That's defined everywhere. This denominator is constant, so no problem here. The only thing that might bother us is this expression here, 1 over the absolute value of x. Of course, this here does have to be non-zero. Otherwise, 1 over x is undefined. For all other values, this expression is well defined, and we can compute a function value. Okay, so the maximum domain of f is df is all reals with the exception of 0, because 1 over the absolute value of x is not defined at x equals 0. I assume there's no questions about this one?
No, so far no.
Good. Okay, so let's have a look at the continuous extension of f to R. So the question is, obviously, f is not defined at 0, but maybe there is a continuous extension for that point. So what we have to do is we have to compute the limit. So we want to know what the limit of f of x is for x tending to 0. And if there is a limit, we could define a new function that is equal to f everywhere but at 0. And at 0, we just define the function value to be equal to that limit. So it's going to be continuous. And that would be a continuous extension. So that would exist if that limit exists. And the question is, well, basically the task is to compute that limit now. Okay, so if we're trying to do that, let's first have a look at this expression. What we can see here is there is an absolute value in there, an absolute value of x. And of course, that absolute value kind of changes its behavior at the point 0. So as we're interested in the limit, as x tends to 0, it might be a good idea to compute one-sided limits. It will turn out this is not strictly necessary here, but as a practice in working with absolute values, I'll still do it this way. Okay, so let's see. Let's try to compute the limit from above first. So that is the limit as x tends to 0 from above, 24 minus e to the minus 1 over the absolute value of x over 2. Now, as x approaches 0 from above, we know that x is positive. And that means the absolute value of x is the same as x itself. Right? For positive values of x, I can just do without the absolute value. So what we can do here is we can just rewrite it as e to the minus 1 over x. And now we're back on known territories. So 1 over x for x to 0 from above, 1 over x tends to infinity. We've discussed that before. So minus 1 over x tends to minus infinity. and e to the minus 1 over x. So this whole expression here, this will then tend to 0, right? E to the minus infinity, so that tends to 0. So basically we're left with 24 divided by 2, and that's 12. So that limit is 12. And of course we can have the very same argument for the other limit, x tends to 0 from below. Let me copy that again. X tends to 0 from below, 24 minus e to the minus 1 over absolute value of x over 2, over 2. Now in this case, we know that x is negative, and for negative x, the absolute value of x is equal to to minus x, right? We have minus 2, the absolute value of minus 2 is minus 2, plus 2. Okay, so we add this minus, and we get minus x as the absolute value. And that means, similar to what we did before, we can now replace that absolute value by, in this case, minus x. Right? Or, to simplify this just a little before we discuss it, that's 24 minus, and here we have minus times minus, that's a plus again. So this is e to the 1 over x over 2. And I need to be careful here again, x is negative, right? That means as x tends to 0, 1 over x tends to minus infinity because x is negative. So this again tends to minus infinity. So we again have e to the minus infinity, well, that's 0. And that means we again get 24 divided by 2, or 12. And of course, one could have known that before, that this case distinction is not really necessary here because we have an expression that involves an absolute value of x, and only that. X just appears in this absolute value, nowhere else. So that means the sign does not really matter, right? Whether x is positive or negative doesn't make any difference to this expression here. So of course you would expect that the value for positive x and the value for negative x would be the same. So both of these tend to 12. And that means both one-sided limits do exist. So that means the limit of f of x as x tends to 0 does exist and is 12. And that means we can define a continuous extension of f at x equals 0. So we can define this extension. We call that f bar. Now that is defined on R because we have just closed that gap in our domain, right? And it's defined as f bar of x equals, well, either f of x, which is 24 minus e to the minus 1 over absolute value of x over 2. And that's true for x in R not equal to 0. Or it's 12. And that is true for x equals 0. And now if you look at that, we know that the limit of f bar of x as x goes to 0 is of course the same as the limit of f of x as x goes to 0, because f bar is the same as f outside of that 0. So the limit has to agree, that's 12. And that in turn is the same as the function value at 0, because we defined it that way. So obviously, f bar is continuous at x equals 0. And because it is composed of continuous functions, it's also continuous everywhere else. also for x in R not equal to 0. So f bar is a continuous function, and thus we have a continuous extension. Okay, before we turn to the image, let's see if there are any questions already.
Yeah, maybe I kind of like tried to answer almost all of them, but maybe like what could be another way to solve this?
Could be another way to solve this.
I kind of like explained that since we are taking, we are dealing with the absolute value and we have the limit when x goes to 0, and specifically the absolute value takes different values when x is negative and positive is like the most convenient way to go. I do not really kind of like recall any other better ways of solving this question.
Yeah, me neither. So, as I said, in this case, I was using this as kind of a demonstration. So what you do is you separate these two cases because you can conveniently express the absolute value in both cases explicitly and then go from there. In this special case, you could also argue that the only place where x appears is here. So it only turns up as its absolute value, and that means the sign of x does not matter at all. So these two limits, if one of them exists, these two limits have to be equal. So it's sufficient to compute just one. That's the only argument I could think of that makes that a little easier. If in doubt, I would always go for separately computing those two, just to make sure. That way we'll always work with the absolute values involved.
There is another question that it says, should we also make notes like the ones in orange to explain our thoughts, or can we assume them as given axioms?
I would make these notes in an exam just to make sure that the corrector, so that I have a means of telling the corrector what I'm thinking here, simply because you might mess up somewhere. You might change a sign involuntarily like I did before. Things like that happen. And in that case, all the corrector can tell from what you wrote there is that's complete nonsense. It doesn't make any sense, and I have no idea what he or she was thinking. If in turn notes like these appear, then at least the corrector knows that was your intention, and that intention was the correct one. And maybe you messed up somewhere. That's fine, but maybe I can still give credit for this. Yeah, so I don't think it takes that much time to write down these little notes, and it makes life for the corrector and ultimately for you so much easier.
Okay, then there is a question that it says, for central exercise 10.3, I split the function up into fx equal to 12 minus the exponential of 1 over x divided by 2.
Let me write this down. So you divide that function into f of x equals?
So 12 minus exponential of 1 over x.
Like this?
Divided by 2. I don't know whether we are dividing by 2 the exponent or the whole exponential. And then I calculate the limit 12 and the limit of the exponential, and then subtracted the two limits respectively. Is this a possible approach?
So if you actually wanted to do it this way with absolute values and with the minus sign here, then yes, of course, you can do that. As long as the two limits exist, right? So if you get something like the result is infinity minus infinity, then that does not mean the result has to be 0 or something like that, yeah? Anything can happen in that case. So this splitting up works if and only if the two limits exist. If they don't exist, you can't split it up. Refer to, what was that? 10.1b, I think, the one with these square roots, right? Sum of square roots. That was a case where we had a limit of the form infinity minus infinity, and it turned out to be 3, I think. And you can't just split it up in that case.
Okay, another question maybe. I tried to answer it like more than once, but probably like it's better to explain it loud. So why the absolute value of x, when x is negative, it becomes minus x. I tried to explain it like different times, like with different examples, but I mean, apparently.
Okay, let's see. So when x is negative, so the absolute value is basically the number without the sign, right? Or if it, in other words, if it has a positive sign, it's just the number. If the number has a negative sign, then it's the number without that negative sign, right? So let's just do an example. If you have like x equals -2, for example, and you want to compute the absolute value of -2, and then of course that is equal to 2, right? You could also express that as saying the absolute value of -2 is -2. So I want to get rid of that minus sign, which I know is there. And I can just get rid of a minus sign through multiplication by -1. So I add another minus sign, minus times minus equals plus. So this is +2 then. So in other words, if I know that x is negative, then that means the absolute value of x must be the same as -x, because x carries a minus sign, right? And minus times minus is again plus. So this is a negative number. A negative number times minus, so minus a negative number, is then a positive number. And that's why this transformation is allowed, right? So what I'm doing here is I'm adding the minus sign to make this negative number positive again. And that is then, of course, the absolute value. I hope that clarifies this idea.
And another question is, if we calculate the limit directly without using above and below method, will the grades will be reduced in the exam?
As long as it works, is correct and understandable, then that's of course fine. There'll be no reductions for that.
And maybe one last one, how can we compute the limit if the root of numerator and denominator is not the same and in the denominator is still a 0?
So if you have an expression, let's say, let's do some example here. If we have a limit like, I don't know, x -1, x +2, and let's say we just have x +3 here, and we want the limit as x goes to 1, something like that. Would you say that's what?
I guess yes.
Okay. Okay, so what we do here is, as x, we want x to tend to 1 here, so we can first try to substitute it. What we get is 1 + 3, that's 4. And here we get 0, and here we get 3. So, of course, that's 0 for the denominator. So something like 4 over 0. And that makes things a little harder, unfortunately. So we cannot just cancel that out. We have a finite limit here in the numerator, and we have 0 here. So what that means is basically as x tends to 1 closer and closer, as it gets closer and closer to 1, this factor here will become smaller and smaller. So the whole expression will get closer to plus or minus infinity. And again, to figure out which of those two it is, if any, we'll have to have a look at the one-sided limits to be sure about the signs, right? So if we look at x to 1 from below, then what we can say here is that as x is close to 1, this here will go to 4, this here will go to 3. So in particular, those factors are positive. This factor here, that tends to 0, and as x tends to 1 from below, so that means coming from values that are less than 1, that means x -1 is going to be negative, right? It's tending to 0, but coming from the negative side. So we have an expression, something positive over something negative times something positive, which is again negative. So the product of those two will also be negative. So we have positive divided by negative, and then that will mean we have a negative sign. And as I said, the values of the fraction are becoming arbitrarily high as x tends to 1, so we should get minus infinity. And a similar argument will work for x to 1 from above. Like this here. So again, this tends to 4, which is positive. This tends to 3, which is positive. X is now greater than 1, so that means this expression, x minus 1, is positive. So we have a positive denominator, and that means we have an overall positive expression. So that whole thing tends to plus infinity. And again, that means this limit does not exist, right? And again, we would have known here already, yeah, then the limit cannot exist, but maybe we could still have got minus infinity. But at this point, even that is not an option anymore, okay? So I hope that clarifies this question.
Yeah, I guess, yes. Maybe one last question and we continue. When answering a question like that in part B, do we have to make the conclusions Dr. Richard did after defining the continuous extension of f? I mean, writing the limit of the extension and the initial function are equal and so on.
So basically what you do is you compute that limit here. So this would be part of an expected answer. Then you should state somewhere that, yes, you can define a continuous extension, and this is what it looks like. And the rest is clear from how you got that, yeah? So you don't have to write down the rest. Okay, so let's say we continue with part C is still missing. Determine the image of the function f. So basically we'll have to have a little look at how that function works. Let's write it down again. F of x is, where is that? 24 minus e to the minus 1 over absolute value of x divided by 2. Okay, so we know already that this function can be extended continuously to the point x equals 0, with f bar of 0 being 12. So this is continuous extension. F bar of 0 equals 12. And now if x increases, so this first point we should look at for x positive, as x increases, we can make the argument that 1 over x decreases, and then of course also 1 over the absolute value of x decreases. And in particular, as x tends to infinity, that will tend to 0. So with limit 1 over absolute value of x for x to infinity tending to 0. And that means we can easily compute the limit of f of x for x to infinity, because that is simply the limit of 24 minus e to the power of 1 minus 1 over x divided by 2 for x to infinity. And as I said, this here tends to 0. So this expression here, this will tend to e to the minus 0 or e to the 0, which is 1. And that means what we get as the limit is 24 minus 1 over 2, or 23 over 2. So for increasing x, the function decreases and it approaches that value here. And obviously the function is continuous, so it will assume every value in between those two. The same argument will apply for negative x. Only saying as x decreases, that again means 1 over the absolute value of x decreases, because as x decreases, yeah, it becomes lower and lower and lower. That means its absolute value increases. right? So again, this fraction will decrease. And again, we can conclude the limit of 1 over the absolute value of x for x to minus infinity. Of course, that must be 0 as well, because due to this absolute value, the sign does not matter at all. So same result. Limit f of x as x tends to minus infinity is also 23 over 2. And the function is strictly monotonous in between, strictly monotone. So what that means is f strictly increases in the interval from minus infinity to 0, and strictly decreases in 0 to infinity. And as f is continuous, that means the image of f is the interval from 23 over 2 to 12, both excluded, of course, because the 12 is also never reached. Yeah, that's only in the extension. So this is the image of the function f. Yeah, so basically, just as a qualitative sketch, what that thing looks like. So here's 12. What that thing looks like basically is it has something like, yeah, it's not very good, something like this. Right, so that is roughly the function f. Okay, any questions on this one?
So to answer the question for image applied generally to functions that might be given, we look at the limits x to infinity and minus infinity from the already computed limit in B.
Just a second. Okay, so that's it, right?
No, there is an answer that it says, so to answer a question. So to answer the question for image applied generally to functions that might be given, we look at the limits x to infinity and minus infinity from the already computed limit in B.
In this case, yes. Yeah, but that, of course, depends mostly on two things. Namely, we need continuity. Otherwise, we can't say a lot, right? If the function jumps widely in between and assumes function values widely off its normal course, then, of course, we can't say anything useful. And in this case, we also need f is strictly increasing first, so here, and then strictly decreasing. And that means this point here, which is never reached, but still, at this point must be a maximum or a supremum to be precise. And these points here, this value here of 23 over 2, that is also never reached, but the function gets arbitrarily close to that because of the limit. And as I said, it's strictly increasing in between. So it can't do something like this, right? In that case, of course, the image would be very different. But that's not strictly increasing in this interval anymore. We need to exclude behavior like this. And of course, we'll get to know more sophisticated methods, which you have probably discussed in school already. Once we get to differentiation, that will become more systematic. So up to this point, we're only able to analyze this for very simple functions, so to say, of this kind.
So I guess this answers, so how can we compute the image without any more information apart from the function itself, or is there a general procedure for computing the image of the function?
So as I said, wait until we get to differentiation. We then have a few more tools for computing the image of the function. But of course, that will only work if the function is actually differentiable. If it isn't, and maybe not even continuous, yeah, then there's no general method anymore.
No more questions.
Which, by the way, doesn't mean it's not possible. It might still be possible, but it will require some different approach, and there's no general recipe for this anymore. Okay, then let's get to the last one, 10.4. Okay, so 10.4 says, show that there are always two antipodal points along the equator, 2 points connected by a line through the center of the Earth that have equal temperature. So let's assume we can have the equator like a line, right? So going once around the Earth, here's this equator line. If we just like work in units of Earth radius, that means we can just start this at 0 and then say, or we could also say we work in terms of the angle, and going halfway around means we have an angle of pi. Going all the way around means we have an angle of 2 pi, right? So basically our equator can be labeled like this. So we start at 0, we end at 2 pi, and of course 0 and 2 pi, this is actually wrapped around in a circle. So these 2 points are actually the same, right? And now we want to look at the temperature along that line. So let's say we have a function that defines that temperature. So that's T. We'll map that interval 0 to 2 pi. We map that to R. That is the temperature along the equator. Okay, then what we actually want to investigate is the difference in temperatures of any given point and its antipodal point. So for a point x, in the interval from 0 to pi, the antipodal point is x plus pi, right? Have a point on that line, you go around another half circle, and then you're just on the opposite side of the Earth. So that's plus pi, x plus pi. This is the antipodal point. And now we can define the temperature difference. Difference between x and the antipodal point x plus pi. So we define a function, let's call it capital T. That is then defined on 0 to pi to r. And the definition of this function is T of x is defined as the temperature at the point x minus the temperature at the antipodal point x plus pi. So if you want to show that there are points where the temperature at x and at the antipodal point x plus pi is exactly equal, then this is the same as showing that capital T has a real root. So we want to show that capital T has a root. And of course, we can easily extend all of that to larger intervals if you just map around, right? So for example, for small t, once we reach the point 2 pi, this is exactly equal to 0, right? So we can just wrap this around and extend the definition of t onto larger intervals by just repeating it. Yeah, once we reach 2 pi, we just jump back to t of 0, and then we walk through this interval once again. And of course, the same is true for t. We can easily extend that into the point pi, for example, and beyond, if we just wrap around the definition of our small t. Now, basically, the only assumption that we have to make here is that the temperature is continuous along the equator. So the temperature doesn't jump rapidly anywhere. That seems like a reasonable assumption, I would say. So we may safely assume, hopefully, that T is continuous. And that does not mean that rapid temperature changes could not happen. They can happen. It's just that there cannot be a jump, right? So there may be a rapid rise in temperature like this, or a rapid fall in temperature, but there's nothing like this. That's the whole point here. So T is continuous, and that also means capital T is also continuous then. Now, suppose we look at T of 0. Suppose T of 0 is positive. Just for the sake of this argument, or we'll talk about the other cases later. Then if that is the case, we can look at T of pi, right? So formally we extend that to pi by just wrapping around. Now T of pi is by definition small t of pi minus small t of pi plus pi, which is small t of pi minus, well, t of 2 pi. And as I said, t of 2 pi would be defined by wrapping it around. So that's the same thing as small t of 0, right? We're on a circle. And that, on the other hand, is the same as minus t of 0 minus t of pi, which is equal to minus capital T of 0. So the temperature difference at 0 and at pi is obviously equal with a flipped sign. So that means if T of 0 is positive, then T of pi is negative. And now we invoke the intermediate value theorem. So we say, well, T is continuous. There is a point with a positive sign. There's a point with a negative sign. So somewhere in between there must be a root. So basically what we have here is this T here. What we say is it has a positive sign somewhere here. So that's at 0. And here's pi. We know that at pi, that T has a negative sign. So whatever it's doing in between, it must at least cross that x-axis here once. And this here is the point that we're looking for, right? That is the root of that function. So what we can now say is by the intermediate value theorem, there is a point, let's call it x tilde, between 0 and pi, with the temperature difference at x tilde being 0. So that's one root of that function. And that, of course, means that the temperature at x tilde is the same as the temperature at x tilde plus pi. So we have found this point such that the temperature at the antipodal point is exactly equal to that. And of course, that did depend on the assumption that T of 0 was positive. If T of 0 is negative, then the argument turns around, because then T of pi is positive. Yeah, we can make pretty much the same argument. So we can conclude T of pi would then be positive, same argument. And that only leaves us with the case that T of 0 might be 0. Yeah, but then of course 0 is the point that we're looking for, right? That means T of 0 is the same as T of pi, and we're done. So this covers all possible cases, and that completes the proof. So let's see what questions you have about this one.
Yeah, there are several questions, like maybe like there are questions related to we also have to solve questions like that in the exam, applying our knowledge to come up with theorems that other mathematicians got famous for, or are there exercises like this in the exam?
Possibly, yes. I will not exclude that. I would probably have added the hint that you can assume the temperature function is continuous. Yeah, I mean, that's an assumption you have to make somewhere, so I would do that for you in the exam, but otherwise it's just a more or less trivial application of the intermediate value theorem. So yes, I would say possibly yes. That might not be the easiest problems, of course, so not all of the exam would be like this, but there might be one or two.
Okay, then can you explain the intermediate value theorem shortly again?
The intermediate, well, the idea is pretty simple. So what the intermediate value theorem says is if you have a continuous function on an interval, like, let's make a quick sketch here. So a function that is continuous, let's start with an interval from this point to this point. And you have a function that is continuous on that interval, whatever that looks like this, for example. Then the intermediate value theorem says, if you look at the endpoints, oops, this one and this one here, and you consider the function values at these endpoints, then these also define an interval, right, in the codomain. And what the intermediate value theorem says is that every value in that interval will be assumed by the function f somewhere between those interval points. So if those are a and b, and if we call that, this series, in this case, this is f of b, and this is f of a. So in this case, f assumes every value between f of b and f of a in the interval from a to b. And again, what you need for that, of course, is continuity. Otherwise, the function could make arbitrary jumps and leave gaps in between. And a continuous function can't do that. That's basically what the intermediate value theorem says. And in this case, and maybe the most common application of that theorem is to show that there is a point, there is a point where the function has a positive value, there is a point where it has a negative value, then that means it will assume every value in between those 2 points somewhere, sorry. So in this case, every value in between those 2 points, and one specific value in between those 2 points is 0. So in this case, that means the function has a root. It has a positive function value, it has a negative function value. So in between those two, it must have a root somewhere. It could have more than one, of course.
Okay.
Anything else?
Yeah. So another question says, how did you get that t of 2 pi is equal to t0?
How did I get that? Well, that's basically an assumption inherent to my model. So what I do is I assume this line here is the equator. So that's wrapped around the Earth in reality, right? Now, let's see if I can make a drawing of that. So I have this globe, and I have the equator around the globe, like here. And then it's wrapped around here. And let's say here's the point 0. We start here arbitrarily. And here we're halfway around, so that is pi. And then we continue our journey. So this is another pi, basically. And here we're back at where we started. So this is the point 2 pi. And that means that's the same as 0 if we work as we're walking around on a circle around the Earth, right? So that's why this wraps around.
And there are no more questions so far related to the exercise. Maybe we can start with the more general ones.
Yeah, discuss a few of those then.
Okay, so there is a question. It says, I guess you can't get away with not answering this question by saying you are a flat earther.
No, you can't. I'm sorry. No scientifically unbased answers like this one are accepted.
Okay, so maybe...
However, you can prove that the Earth is actually flat, and then that make a basis of your answer. That would be fine. But you have to prove that. There's no credits for beliefs.
Yeah, so more general questions, like the first one is, how about using colors in the exam? For instance, red.
Don't use red. So the answer is pretty simple. Don't use red, don't use green, because these are the two colors that our correctors will use. And you will have a hard time, and we will have a hard time, telling apart corrections and your answers. So red and green are explicitly forbidden. Any other color is fine, as long as, of course, your method of scanning supports that. So if you refer to a blue line and your scanner only works in black and white, then you might not get credits for the non-existent blue line. Yeah, so please make sure your technology supports colors. If you do that, that's fine.
Yeah, okay, so another general questions is that I have got a general question regarding continuity. If a function like the sine is obviously continuous, can we just state that, or do we need to prove it?
So we've discussed continuity for a number of functions, and of course you can just use that result. There is also a number of functions that we have not discussed. So the basic functions like sine and cosine. And again, you're free to use continuity for those. We mostly avoided trigonometric functions up to this point. Unfortunately, they can't be avoided all the way. But yeah, if that is necessary, you're good to just state that these basic functions are continuous.
Okay, then would it be possible to share the solutions of the remaining problem sheets at a little earlier?
Yes, I will do that. So usually I'll try and share the solutions of the remaining problem sheets once the central exercise is over. So after this central exercise, I put up all solutions for sheet number 10. Please keep in mind that especially the solutions for the homework problems are meant to be preliminary at this point. So I might change those once we had the tutorials and once I got feedback from the Q&A sessions to maybe clarify a few points or add some explanations, or maybe change the method of solution if I found that those was confusing for you. So you might want to re-download an updated solution later if there's an update. Please watch out for that.
Okay, and where can we find the solutions for the 2017 exam?
The 2017 exam, so the solutions that I have, I posted those as well. If I didn't post it, I don't have a solution. So I don't know. Feel free to post one to the forum.
A different question is the quiz 10 not only about the videos from last week, but also the videos from this week? If so, could we maybe keep the quiz open longer so that we can do the first questions this week and the questions to the new videos next week?
I need to forward that to the quiz master. Actually, I don't really know that.
Okay, so now suddenly the chat got very busy. So in 10.3c, 12 is excluded in the image, right?
Yes, right.
Then,
that was the question?
Yeah.
Simply because that point is not included in F, right? So that's only a point that is assumed in the continuous extension, and it would be in the image of the continuous extension, but F never assumes that point. It's just not defined at 0, so 12 is not assumed.
Okay, now I'm going to read them as they come because I didn't have the chance to read them before.
Yeah,
but on the past exams you have provided us, there weren't any transfer exercises like 10.4. So you are planning to introduce those harder problems for our exam?
I wouldn't say there were any transfer exercises in those old exams. I'd state that, yes, there were hard. And I mean, if you look at the results, which you can't do, of course, but what I could do, there were some really hard problems in those exams. If those seemed easy for you, then I guess you're good to go. You don't have to worry about anything.
Then just wanted to know if the professor had time to look into the 1 plus 2 plus 3 plus 4. I guess this is the YouTube video. I didn't. I'm sorry. I just forgot about it.
Yeah, me neither. I'm sorry. I'll have to have a look at that sometime this week.
Yeah,
Too many other things happened last week.
Maybe we can bring something next Monday.
I hope so, yes.
How important are proofs for the exam? In the lecture of this week, it was shown how to compute the derivative of the exponential function. Do we need this proof, or is it enough to know the derivative?
So specifically for the exponential function, you don't need to know the proof, but of course you should be aware of that method of arriving at a derivative, and you should be able to, at least in easy cases, prove that a function has a derivative using this definition. So you should be able to apply that, yes.
Will we be provided a mock exam?
Yeah, right. I wanted to make an announcement on that. Good. Thanks for reminding me. Let me have a quick look at my notes, and I'm going to announce that on the forum as well, so you have it in writing. So problem here seems participation in the quizzes is down. So you were doing pretty good in the beginning, but the last 2 quizzes or so, participation really plummeted. So it's not looking good for that. So I decided, I discussed that with the tutors and the quiz masters, and we decided to give you another chance. And specifically, the requirement will be for the quizzes 10, 11, and 12. Let me write that down, actually. For the quizzes 10, 11, and 12, I want to have at least 300 students participating. So that is not even 50% of you. I want at least 300 participants, and I want an average performance of at least 70% among those participants. And I guess you don't see my screen, right? Need to start the screen sharing again. But once again, I'll have that on the forum as well. Okay, so there will be a mock exam if these conditions are satisfied. For the last 3 quizzes, 10, 11, 12, at least 300 participants each, of course. And an average performance of at least 70% each. That should be something that you can do, especially considering that many of the topics that are on those quizzes should be familiar, more or less familiar from school. So I think that should be doable. Let's try it this way. If that works, so if you satisfy these constraints, then there will be a mock exam.
Okay, so next question is, will we get the solutions to the 2017 exam? I want to check my solutions and see if my approach is right.
Yeah, again, solutions I haven't posted, I don't have.
Maybe like if you have a specific question in a certain exercise, maybe post it in the forum and then we can try to go from there.
Of course, feel free to post your questions regarding the exams on the forum. Also feel free to ask during Q&As and also during the tutorials, of course. If you have a suggested solution that you would like to offer up for discussion, then also feel free to post that to the forum. Maybe other people will be able to spot your mistakes.
Okay, now could you please show C10.3b? I am not sure I copied it right, and maybe I have a question.
Sorry, 10.3. So you mean in my notes here? 10.3.
Part B.
Part B. That is quite a few pages. Which one would you want? I'll just scroll through those slowly while you ask the next questions.
Are we allowed to do the exam on the iPad by downloading it and writing with the Apple Pen, for example, in GoodNotes?
Yes. Yes, you can use electronic means of editing the PDF.
And I guess that's it.
Okay, wonderful. Let me just scroll once again.
Nevertheless, they will also get the solutions of these.
Of course, yeah. I'll upload those in a few minutes, I hope. Probably somewhere around the end where you missed something, maybe. So I guess we're approaching the end.
Multiple choice questions in the exam which will not need justifications.
There might be questions that do not require justification, but usually no multiple choice questions. And if I don't require justification, I will explicitly write that in the problem statement.
How come there a negative how come there are negative values in 10.3b if it is the absolute value?
Which one are we discussing? So where exactly do you have these negative
I
values?
guess what they mean is it's the same thing like when x is negative, then the absolute value of x is equal to minus x. I guess like this that it has been already explained.
Possibly. Where was that? Somewhere here, right? So here, for example, we have x that is negative as it approaches 0 from below, and that means the absolute value is minus x, which of course is positive. So this is a positive value. If x is negative, then minus x is positive. So there are not actually negative values involved here. So that's all?
That's it. Yeah, I think we can finish it here.
Okay, great. So thanks once again to Lissuri for moderating. Thanks to you for all your questions and for attending the central exercise session. As usual, I hope to see you in the tutorials in person, more or less in person. And otherwise, I hope to see you next Monday. So goodbye.
Ciao.